In this discussion, I want to look at a few minor issues involving the intent statement and subroutines, and also we're going to look at how to fix Newton's method more or less in the event that you have a root of multiplicity larger than 1. I've written several programs with beginning of the name SIDE, numbered 0, 1, 2, 3, and 4. I've already compiled them, so I can save a little bit of time on this. I want to look and see what side 0.f90 looks like. This basically does the sort of thing we've done before. I have an integer I. I'm going to go around in a loop for I equals 1, 2, 3, 4, 5, and 6. For each one of those I values, I'm going to print out the square root of I. As you recall, the square root function expects to receive a floating point value, so I use the real I comma kind equals 8 to convert the integer value into a floating point value. As I said, I've already compiled these things, so I'll just run this one. And as you can see, we get square root of 1, square root of 2, square root of 3, square root of 4 is 2, and then square root of 5 and square root of 6. I want to look at the next one, which I've called side1.f90. Now, this is interesting. I've got a loop index, I, going from 1 to 6. Ordinarily, whatever is in the interior of the loop gets executed, then the value of I increases, and then the action is repeated. But as you can see in this example, I'm doing something really odd. I got a loop going on. The loop counter is increased by 1 each time through the loop, but on the other hand, I'm literally decreasing the loop index by hand with the I equals I minus 1 statement. So it'll be interesting to see what the compiler has to say about that. So let's try to compile that program and see what it says. It doesn't like it. Any reasonable programming language will forbid you from messing with the index of a loop within the body of the loop. Doing that could cause all kinds of confusion and poor behaviors. So generally speaking, if you have a looping structure, you are not allowed to mess with the index in the interior of the loop. I'm going to make a minor modification of that program, and in this case, rather than having the square root of the real version of the integer being calculated in the main program, I'm just going to print out f of I. F is a real kind equal 8 function. I feed it an integer. I don't have to call it I down here. I can call it something else, which I will for variety. I'm going to calculate the square root of the kind equal 8 floating point version of j. That's going to be stored as the function value. So when I print out these function values, I'll be printing out square root of 1, square root of 2, through square root of 6 again, except it's not being computed in the main program. Having already compiled the program, I'll just run it, and of course, we get what we expect to get. I'm going to make a minor modification of that, except this time, down in the body of the function f of j, I'm going to decrease the j by 1. It'll be interesting to see two things. Number one, will the compiler accept this? And number two, what's going to happen when I run this? The -o side 3 says put the executable in the file side 3. You'll notice that it compiled without any trouble, which is ominous by itself, but let's run that. It's still running, and apparently it's never going to stop. Over on the Unix side of things, I can make it break by saying Control-C. Let's go back in and see what's going on here. From a practical point of view, this is doing what we were trying to do before. We're decreasing the loop index, except now it's obscured enough away from the main program that the compiler doesn't detect it. So at the beginning of this loop, I is 1, and we print star comma f of I. If that's all that were going on in that function, that would be fine, but the input is decreased by 1, so j at the end of the first function call is 0, but j is the same as I, so when I go back up to the main program, I has been set equal to 0. Then, when you go around in the next loop iteration, I is increased by 1, so I is now 1 again, and then the same thing happens over and over and over again. Functions should not have side effects. Functions should not change the value of any of the inputs into the function. So what I've written here is really bad code, but it is legal code. The compiler will accept it. We don't want to allow things like that. Somehow we want to forbid function f from changing the value of j, and this is what I'm really wanting to talk about in this first part. I want to look at this file, side 4. It's the same thing as we had before. It has the correct computation of f, then it has this terrible thing that I should not do, j equals j minus 1. But the point of what I'm trying to talk about is the mechanism by which I forbid function f from changing j is right here in the declaration. Integer, comma, intent n, colon, colon, j. That tells the compiler, look, whatever you do, function f is not allowed to change the value of j. So this sort of lets you go back and forth between call by value and call by reference. You can do a lot of other interesting things with intent, but for now at least, intent n is the important thing for us. The punchline is the compiler should refuse to compile this now, because I've literally told it, function f, you are not allowed to change variable j. So I'm going to try to compile this. I'm going to try to put the executable in the file side 4, but it's no use. The compiler, having seen that intent n, looks at that j equals j minus 1 and says, no, I'm not going to let you do it. If you're sending information to a function or one of these other types of program units that we'll talk about, if you know that you're not supposed to let that program unit change the value of one of the variables, all you have to do is to declare it with intent n, and you can't make a mistake then. Aside from the general syntax of the language, two of the most useful things you can say are implicit none and intent n. I want to look at some programming issues related to our bisection and false position code. I've gone back and changed this to bisection, so even though the name of the program is false position, we're actually using bisection. So I'm going to have real kind equal 8 for all of my floating point variables. On this system, kind equal 8 means double precision. As you have found out on your system, it may be a different number for the kind, so be aware of that. I'm going to have A, B, M, and F as floating point numbers. I'm going to have one-dimensional arrays, A values, B values, and M values. These are allocatable arrays, so I don't have to tell you up at the top how big they are. Also, I'm going to have a loop index I and an integer variable n steps, which is going to indicate how many steps of the method that I'm going to do. So again, I'm using my square root of 2 example as something to get started with. I'll set A to 0, B equal to 2, and the midpoint of that interval is A plus B over 2. As I've mentioned several times, I don't like that way of calculating M. We'll take care of that by the end of this discussion. Then, the user is asked, how many steps of bisection do you want to do? So you read this in from the keyboard. After you know how many steps you're going to do, allocate your arrays. A values, B values, and M values will be one-dimensional arrays with indexes that go from 1 up to n steps. Most compilers, when you allocate memory like this, sticks zeros into them, but some leave whatever random. That is to say, having had an internet outage, some compilers will stick zeros into newly allocated arrays. Others leave whatever random electrical garbage was sitting in RAM at the time there. So I'm going to set the entire array A values equal to a bunch of zeros, and then do the same thing for B values and M values. This way, there's no chance of me confusing myself. I'm going to set A values 1 equal to A, B values 1 equal to B, and then I'm going to calculate the midpoint at the next step, at step number I. The next one would be I plus 1. I'm continuing to calculate this midpoint in a rather bad way. We haven't figured out why that's bad yet, but we will shortly. Then if the function value at A, number I, times the function value at M plus 1 for the midpoint, number I, which we just figured out a minute ago, is less than 0, then my new bracket is going to have the same A value as the previous one, but the B value is going to become the midpoint that we just calculated. Otherwise, it's the other way around. I had to pick some way of indexing these things. I picked it this way. I'm sticking to it. After I'm done, I'm going to print out from 2 to n steps the midpoint values and the function values that go with the midpoint values. I'll go around in my loop, print out my output, deallocate my memory, and that's the end of my program. My real function, f of x, is still x squared minus 2. So I'll compile this, and then when I run it, it wants me to tell it how many steps of bisection to do. Just for illustrative purposes, I'll say 12. And as you can see, the midpoints appear to be rapidly approaching square root of 2. If by rapidly I mean the kind of stuff you get in bisection. In the next version, false3.f90, I'm going to take the guts of the bisection method and remove it from the main program, and I'm going to put it off in its own program unit, but it's not going to be a function this time. It's going to be a subroutine. So we have, as usual, our program, our implicit none, the declarations of various types. We set A and B equal to their initial values. We calculate the midpoint still in this way that I don't care for. Everything is the same as before, except where I had the loops to actually do the bisection method, instead I have this statement that says call bisection in steps A values, B values, and M values. This subroutine, bisect or bisection, is going to carry out the calculations needed for the bisection method, but it's not going to clutter up my main program. It's going to do all of the work for the bisection. When it comes back, I'll print out the midpoint values and the function values that go with the midpoint values. I'll deallocate my memory, and that's the end of my program, except for initializing stuff. That's my main program now. The rest of it's just sort of bookkeeping. Function f is still x squared minus 2. Here's how we do our subroutines. It's a program unit, like a function, except unlike functions, subroutines don't return values as such. Any communication between this subroutine and the calling program unit has to come through these variables. Now, in steps should not be changed by the subroutine, so I'm going to declare it this way: integer common intent n in steps. That makes it impossible to even by accident have bisection change the value of n steps. I'm going to need an integer I as my loop counter. I don't declare that intent n for two reasons. Firstly, it wasn't sent in to the bisection routine from outside, so that wouldn't even make any sense. But more importantly, I do want this subroutine to be able to alter the value of I, because I'm going to use I as my loop counter. If you look at what you have here, we calculate the midpoints in this way, again, that I don't like. We do the if, then, else. We go around in the loop. This is the end of the bisection method, the actual work to do bisection is this work. This is done within subroutine bisection, and after this is done, we have end of the subroutine. If I had more subroutines or more functions, I could put them after this end. So nothing has changed, except I've made a subroutine called bisection. It receives number of steps, A values, B values, midpoint values. I dimension these arrays as they are up in the main program. F is the function f of x equals x squared minus 2 that we're trying to find the zeros of. I need to declare that here because if I don't, this implicit none makes f undefined. The subroutine won't know what kind of thing it is. But other than the bookkeeping details, this is just a simplification of my original program. My main program now looks much less cluttered than it used to. All that's in the main program is initializing stuff, calling the bisection subroutine, and then printing the output out, and you're done. So we'll compile this, then we'll run it. We'll do 12 steps of bisection, for instance, and we get the same numbers that we had before, of course, because we're doing the same calculation. We're just organizing it differently. We're going to make a modification here. Let me go up to the top of my program. That first m, I meant to change that, but I didn't. So the initial m I'm calculating is a plus b over 2. That doesn't hurt anything because I don't actually use that m for anything. Everything is exactly the same. There's my f function. But in my bisection code, I'm going to calculate the midpoint in a different manner than we did before. So this bears some talking about in the mathematical sense. If we're doing bisection or the method of false position, the width of the interval that we're working with is going to get small pretty quickly. I want to pretend that I'm on a computer that out in main memory can store 3 significant figures. So this is A and this is B. As we've often said, internally the processor may have more digits than that in its special purpose registers. So inside the computer, inside the processor, not yet written out to memory, I'll think of my A as being 0.996 and 3 zeros. When I want to store this out to main memory, I'll have to get rid of these last 3 digits some way. Either just chop them off, or what people actually do is rounding. I'm going to add these 2 numbers together. This is the top of the fraction in m equals a plus b over 2. Let's see what happens. 0, 0, 0. 6 and 9 is 15, so carry the 1. 10 and 9 is 19, carry the 1. 10 and 9 is 9, and we have the 1 on the outside. I've got a problem now. We say our numbers are normalized if we write them as a decimal point, a first digit that isn't 0, and then the rest of the digits. And see, this doesn't look like that because of the 1. So what I can do is I can shift these digits to the right one place. 1995, 0, 0 times 10 to the 1 power. And then when I store this out to memory, I have a real problem, a serious problem. I can only store 3 digits, and I've got 4 of them. Even worse, that digit is 5 or more, which means if I want to round this, I've got to round the 9 up by 1, which makes it a 10, pushing the 1 over onto the next thing, which makes it a 10, pushing a 1 over onto the next thing. When I write this out to memory, it's going to be 0.200 times 10 to the 1 power, which is 2. And then assuming that I can divide by 2 exactly, that would be 1. So because of the way the computer is doing its arithmetic, if I literally do this, this is going to happen to me. So look at that. We have calculated the average using the formula that we think we ought to use. And due to the way the computer does its arithmetic, the computed midpoint of this interval is actually outside the interval. This would wreck the method of bisection if you calculate the midpoint incorrectly. And this sort of thing is liable to happen to you as the width of the interval becomes very small. So we need some way around this somehow. I claim that the expression a plus b over 2 and the expression a with half of b minus a, I claim those two numbers are the same number. It's not very hard to see because a is 2a over 2. When I add the tops together, I have 2 times a plus b, and then when I subtract the a, I have a plus b over 2. So these two things really are the same thing if we're doing exact mathematics, if we're doing exact arithmetic. As we've seen though, if you calculate your midpoint in this format, you are liable to jump out of the interval that you want to remain in. I claim that this is a much better way of doing this. Why is that? For example, in the problem that we're looking at, both a and b are getting close to square root of 2. So these kind of numbers are 1.414 some odd plus b minus a over 2. If b and a are very nearly equal to each other, which they will be if the interval has shrunk down far enough, this number is going to be very small compared to this number, and in the computer, you'll get a back for an answer, which of course is not exactly what you would like in exact arithmetic, but on the other hand, it doesn't jump you out of the interval either. So from a numerical perspective, this way of calculating something is superior to this way. And remember, we said you never take two numbers that are vastly different magnitudes and add them together or subtract them. Unless you're doing it on purpose, which we are here. This will help our methods converge numerically. So down here in subroutine bisection, I am not going to calculate the midpoints the way I've previously calculated them. The new midpoint value is going to be the previous a value plus the previous b value minus the previous a value over 2. And we're doing this, as we said, for a very specific reason, to avoid any chance of this jump out of the interval business. That's half of my refinements. I am still deciding which clause here gets activated by multiplying two function values together. We're going to have to talk about that next. So we'll recompile, and then we'll run the thing. We'll do 12 steps of the method, And we get the same answer that we got before. The problem that we're looking at here is an extremely nice, pleasant, easy to deal with problem. It doesn't cause us any of the issues that we're talking about, but our code is slowly becoming more and more bulletproof as we go along. The way that we've been deciding which half of the interval to retain and which half to throw away has been this. We calculate f of a times f of the midpoint and see if that's less than 0 or not. If it is, I should make b equal to the midpoint, and I'll have a bracket, a pair of numbers between which the function value has to be 0 somewhere. And if that isn't true, I should set a equal to m, and then this should cover all cases, except of course the possibility that one of them is equal to 0. That still hasn't been taken into account, but there's something worse about this. We're trying to solve f of x equals 0, and a, b, and m are all supposed to be getting very close to the place where f of x is equal to 0. So as I'm going along, both f of a and f of m are getting really small in magnitude. So for example, maybe f of a is 3 times 10 to the negative 250 power. You might think this can't happen, but it does. And maybe f of m at our computed midpoint is negative 2 times 10 to the negative 250 power. In the computer, f of a times f of m is going to be negative 6 times 10 to the negative 500 power. In double precision, the smallest number that you can have other than 0 is about 10 to the negative 308 power. So this number is distinguishable from 0 by the computer. So is this one. But when I multiply them together, 10 to the negative 500 power is much closer to 0 than it is to the first non-zero floating point number. In the computer, if this happened, f of a times f of m is going to get evaluated to 0. And see, now I've got a problem. These function values have opposite signs. So logically, I want this to be executed and not that. But if I do what I've got here, then f of a times f of n gets computed as 0. 0 is not less than 0. The thing that should get executed doesn't get executed, and the thing that does get executed is the thing that shouldn't. We will have made the wrong choice in the bisection method. Now, some people think that you could easily fix this because they think, well, you're getting the 0 there. That's the problem. Just change it to that. Doesn't work. Suppose f of a was 3 times 10 to the negative 250 power, and f of m is positive 2 times 10 to the negative 250 power. F of a times f of m is going to evaluate to 0. So if you're thinking of fixing it like this, then this will get executed, but that won't. But that's no good. F of a and f of m have the same sign. I don't want that to get executed now. I want the other one to be executed. The way we fix this up is we re-express everything in terms of things that cannot experience underflow. That's what we've got to do. So I'm going to make one last refinement to my code. It's going to fix both the possibility that you've landed right on the answer, and it's going to prevent this floating point underflow, which could cause you to make the wrong choice in your algorithm. I'm going to have two new integer variables, one of which is called sin A, and the other one of which is called sin M. These are going to be integers that represent the sign, the positive or negative sign of A, and the sign of the midpoint. I'm going to have something else new. I'm going to have something called check sign. Check sign is going to be a function. It's going to be an integer function. It's going to take on values 1, 0, and -1. And let me show you my check sign function. Integer, function, check sign, z, implicit none, real kind equal 8, z. I should have put comma intent n in there, so I can't accidentally change the value of z, but never mind that. If z is positive, check sign is going to be 1. If z is negative, check sign is going to be -1. If z is exactly equal to 0, then check sign will be 0. It may be unlikely, but that could happen. Instead of multiplying f of a and f of m together, I'm going to multiply check sign of f of a and check sign of f of m together. That's going to be a product of two integers, each one of which is either 1, -1, or 0. If the product comes up equal to 1, that means that it's either 1 times 1 or -1 times -1. That means that the function values had the same sign. If that quantity comes up -1, that means the quantity was either 1 times -1 or -1 times 1, indicating that f of a and f of m had opposite signs. And if check sign comes up equal to 0, then the product of the two things is going to be 0, and that's going to tell me, unbelievable though it might seem, that I've landed right on the answer. So instead of doing what we were doing before, I calculate my m values in the same way that we did previously, the new and improved way. Sin A is check sign of f of the a value that we need to look at. Sin M is check sign of f of the m value that we were looking at previously. So instead of saying if f of a times f of m is less than 0, we'll say if sin A times sin M is less than 0, note the 0, not 0.0, because these are integers, then that means that the B needs to be changed and the A needs to be left alone. Otherwise, it's the other way around, unless I happen to land on the answer. So right before I do this check, right before I do that, I check and see if I've landed on the answer or not. If the product of sin A and sin M is 0, at least one of those is 0, which means either f of a is 0 or f of m is 0. What I'm going to do in that case is I'm going to print out the f of a and f of m value and then issue the return statement. Unlike what goes on in C and C++, return here doesn't send a number back as such. It just says go back to wherever it is you called this subroutine from. If this happens, we're done because we found a place where the function value is 0, either a or m. If this doesn't happen, then the sine a times sine m is either 1 or -1, and I can use its plus or minus sign to decide which clause that I should execute. So we'll compile the thing. I forgot to put it in a file other than a.out. So I'll just run a.out. How many steps do you want to do? 12. So things are as they have been before. The code is not bad at this stage of the game. It can detect most things that happen, but there's one other thing I want to look at. In my subroutine, Bisection, I'm going to send it an additional variable called steps done. Now, if I change this subroutine header here, I have to change it up in the main program in a likewise way. Steps done is going to be an integer variable, and it's going to tell me how many steps of this method that I did before I decided it was time to quit. Because as A and B get closer together, there are fewer and fewer floating point computer numbers between them. Eventually, you're not going to be able to make this bracket that we've been working with any smaller than it already is. So at the end, I'm not going to print out from 2 to n steps. I'm going to print out from 2 to steps done. Down in the subroutine, I'm going to set steps done equal to the number of steps. It could be that my method is going to run all the way to n steps iterations without the brackets ever going into this locked down pattern. So unless I know differently, steps done will end up being n steps. And what I'm looking for is if the old and new a values are exactly the same and the old and new b values are exactly the same, that means the bracket at the step I'm looking at now is the same as it was at the previous step, and it would be ridiculous to go on and do anymore. I'm going to set steps done equal to I, which you'll remember is the loop counter for my main loop. So what this will do to me is it'll detect if the bracket is changing anymore. Now, since I'm only doing 12 steps of this, I don't really expect to see this bracket not changing anymore thing. And indeed, if you look at the numbers, I don't see that happening. But what I can do is I'm going to pipe the output through less so that it doesn't go flying off the screen. How many steps do I want to do? 2,000. You can't see it, but I typed 2000 and hit enter. And it said, bracket is unchanging at step 54. It's done 54 steps of this stuff. And by the time you get down to step number 54, the computed x squared minus 2 is about 4.4 times 10 to the negative 16 power. So at step number 54, that last midpoint, it should be a very good approximation to square root of 2. If you remember, one day we did a rough estimate and said that it was going to take roughly in the 40s to 50s steps of bisection to make this work. This is what we see. So not only can I safeguard jumping out of the interval and safeguard against wrong decisions based on floating point underflow, I can also build in something that tells me that it's nonsense to go on anymore. In this case, it's nonsensical to go on past step number 54 because the bracket isn't changing anymore. Usually in our numerical methods, in our course for 4670, 5670, we write things in a very simple way. But what I've been wanting to show you in this discussion is several different types of ideas that you can use to make your program more bulletproof than it would otherwise be. There are other things that we could have done to make our program even more robust, but beyond a certain point, you hit a point of diminishing returns. So I hope this has been somewhat informative. And now to finish, I want to talk about the modified Newton method. We have looked explicitly at a toy problem of type f of x equals a constant a times x minus r raised to the m power, where m is a positive whole number larger than 1, so that r is a root of multiplicity, m bigger than 1. We've previously seen that the error at step number k plus 1 in our toy problem is going to be 1 minus 1 over m times the error at step number k, and we lose the quadratic convergence that Newton's method had. Basically, this is because g prime at the solution is not 0 anymore. I want to investigate a very simple way that you can sometimes repair this situation. So we're going to make a new method. I'm going to have alpha number k plus 1, x number k plus 1 equal x number k minus some constant alpha times f at xk over f prime at xk. If alpha were picked to be 1, this is just Newton's method. If alpha is not 1, we're going to call such a method a modified Newton's method. And what I want to see is this: if I pick the alpha correctly, can I make g prime at r equal to 0 again? Because that is what ultimately led to the quadratic convergence of Newton's method. So our fixed point function is g of x equals x minus alpha, f prime of x on the bottom, f of x on top. Now, we are modeling the behavior of these methods close to the root of multiplicity m by pretending our function is a times x minus r to the m. The derivative of that is f prime equals a times m times x minus r raised to the m minus 1 power. We need to put this in to write out a formula for our g function. So if I literally write in for f of x, a times x minus r to the m power, and the derivative on the bottom is a times m times x minus r to the m minus 1, we see that firstly, the a's cancel out. Secondly, I'm going to have an m on the bottom of the fraction. So g of x is x minus alpha over m. I'm going to have m factors of x minus r upstairs and m minus one of them downstairs. So this would be one factor of x minus r left. For the toy problem, which we are using to model the behavior of roots of multiplicity bigger than 1, close to the root, this is how we'll model our g function. I want to calculate the derivative of this. G prime at x is 1 minus alpha over m multiplied by the derivative with respect to x of x minus r, which is 1. So g prime at x is 1 minus alpha over m. This is not 0 for most choices of alpha, therefore you get linear convergence. But if you're extremely sneaky, if you let alpha equal to the multiplicity of the root, then g prime is 1 minus m over m, which is 0. And if you remember our Taylor series expansion, that means that the convergence of this method close to the root of multiplicity m is going to be better than linear. It's going to be at least quadratic. So if I somehow knew what the multiplicity was, I could easily write this new method down. X number k plus 1 is going to be x number k minus the multiplicity of the root times f of xk over f prime at xk. This is going to be what we'll call our modified Newton's method. If you were using Newton's method to find some 0 of a function, and you observed the progress of the function values and saw that they were getting smaller in size, as you would like, but they're not getting smaller very fast, one of the first thoughts that would occur to you is that you have a root of multiplicity bigger than 1. If you take m to be 1, you're just doing Newton's method. If what I just described happened to you, you might try changing the m to 2 and see if that improves things a great deal, or to 3 or to 4. If you start close enough to the root of multiplicity m, when you finally hit this correct m, convergence should become very rapid because the g prime is going to be 0 then in the toy problem. So this is how you can partially, anyhow, fix the bad convergence of Newton in the presence of a root of multiplicity m.